Welcome back to another video on the Unit 2 test. And this video will pick up with question 68, the last question on page 4 of the test, dealing with our heating curve of water. Question 68, one of the following statements is false. First of all, they're saying moving from E back to D, condensation is occurring as heat energy is being loaded. So we're looking at the graph. Moving E back to D. There's E back to D. So we're going this way. So energy must be decreased. So right here, it is a gas. We're decreasing energy, pulling energy out of the gas. It's going into the environment or surroundings. That's called condensation. So what happens is from F to E, they're lowering the energy, slowing the molecules down. They're lowering the kinetic energy. At point E, the molecules are moving close enough together and slow enough together that the intermolecular attraction between them goes up and they begin pulling together back as a liquid. That is a nice, strong, stable intermolecular attraction. So that is going to be an exothermic process where energy is released. So going E to D would be exothermic, energy is being released. And that process is called condensation, and energy is being removed or released. Moving from C to B shows you that freezing, and they said was endothermic. So we're looking C back to B. So C, it's a liquid. D to C, they're slowing the liquid molecules down. So at point D, it's now a liquid, and they're lowering the speed of those molecules. The temperature is going down. So the liquid molecules begin slowing down, and now they're going to start lining up in a solid. When we have water, the liquid molecules can move around each other close. So the density is high. When they start to freeze, they begin lining up this way and start spreading out. That's why the density of water as a solid is less than the density of the water as a liquid. As a solid, they take up more space. But at point C, freezing starts because they're now lining up. The process of freezing is exothermic. Going from C to B, the energy is going this way. That's lowering, not increasing. So energy is being released. Some of that potential energy of the molecules in the liquid state is being released as it lines up into that nice, stable, neat, solid structure. So moving C to B shows you it's endothermic. No. You have to pull energy out of it. We're going this way. C to B is going this way. So on this axis right here, we're going this way. That is a lowering of the energy, not an increasing of the energy. Lowering of the energy means it's going out into the environment. That's exothermic. Moving from D to C, the temperature would decrease. Oh yeah, temperature's going down. Here's D, there's C, temperature went down. The motion of the molecules is slower. The graph slopes down from D to C, then levels at point C because freezing has been reached. So D to C, we're slowing them down so much that they are now able to start lining up. They're no longer able to move by each other, which liquid molecules do. They start pulling together in that solid pattern. Freezing has begun. The potential energy is released from E to D. So E to D, E to D. As we go from E to D, the line's not dropping. So kinetic energy is not going down. Yet the energy is going down. It's not kinetic energy. It must be potential energy that's going down. And the molecules once again are being pulled together in the liquid. So the intermolecular forces arise, making it a nice stable liquid structure. They're not able to fly around like they could as a gas. The potential energy is lower. That would be true. All right, now we move on to our final page. Our final page is dealing with this chromatography right here. Here's the chromatography paper right here. Here's our little graph. Here's where the spot was made, and the solvent traveled up to the paper to this line right here. Question 69, what's the RF value of the number 69? What 69 is pointing to? So here's number 69 right here. Let's see where it's pointing to. It's pointing to right there on the graph. And they're asking what's the RF value? The RF value is the ratio of how far the color went compared to how far the solvent went. So it's distance the color traveled divided by distance the solvent traveled. It's pointing to right here. It's this yellowish color. The yellowish color went up about, what is that, 5.5 centimeters. The solvent was 6.2. We look over here, 5.5 divided by 6.2 is 0.89. So which of these is closest to 0.89? Letter D, xanthophyll is closest to 0.89. Number 70, what's the RF value of what the number 70 is pointing to? Here's my number 70. I go up and over. It looks like it's about 1.4. That's where the line's pointing to. So we're looking for this darker green color. That color went up the page about 1.4 centimeters. The solvent line is right here at 6.2. 1.4 divided by 6.2 is about 0.225. Which of these numbers is closest to 0.225? Letter A. That's chlorophyll B. Chlorophyll B, letter A. Which pigment is not on the chromatography? Well, we already know chlorophyll B is on there, so we can cross that one out. We know xanthophyll's on there. We can cross that one out. We have to find out what the other colors are. What's the RF value of this color right here, this light green? Well, that color went up about 2.9. We're looking about the middle of it. The solvent went 6.2. This color has an RF value of 0.467. 0.467 is very close to chlorophyll A, so we can eliminate that one. So we've eliminated A, B, and D. Those are all on there. So we did this color, we did this color. The only one we haven't done is this little yellowish orangish or yellowish pinkish band. It went up to about 5.9. This band is a different color. It went up to 5.9. We dropped, the solvent went up 6.2. So 5.8. I called it 5.9. 5.8 divided by 6.2 is 0.935. Yeah, I guess that could be somewhere in there. 0.935. 0.935 is very close to 0.94. That's carotene. So this one's on there. Chlorophyll A is on there. Xanthophyl's on there. Carotene's on there. Anthocyanin is not on there. None of those have a 0.6. Now it's telling us the anthocyanin is the red color in maple leaves. It has an RF value of 0.60. There we go, in isopropyl alcohol. And that's the solvent used here, isopropyl alcohol. What month of leaf was this? Well, anthocyanin, they told us, is a reddish color, which is the color that we see in leaves in the fall, late summer and early fall. Well, that one's not in there. What do we have in here? Lots of greens. This leaf must have not been harvested in September or October, or we would have seen anthocyanin. It's certainly not a spring leaf. It's certainly not a summer leaf. Why? Because it doesn't have the red color of fall in the leaf. Number 73, chlorophyll A has an RF value of 0.46. What color is it? 0.46. Well, there's the RF value of 0.46. We go up and over. It's a light green or even a yellow green. It's a light green or even a yellow green. 74. Which pigment is more attracted to the solvent and least attracted to the paper? The one that's least attracted to the paper is going to go up the paper the furthest. What's pulling it up the paper? The solvent. So the color that is pulled up the paper the greatest distance is the one that's most attracted to the solvent, or it wouldn't be pulled up the paper with it. So we go over and down. That was the carotene. That's the 0.935 or 0.94-ish. That's carotene went up at the furthest. That's most attracted. And the last question on our test, which statement is false? Large RF values indicate that it's more attracted to the paper. In order to have a large RF value, it has to be going up the paper the furthest. So the ones with the biggest RF value is 0.935 or 0.94. That's the one that's most attracted to the solvent, least attracted to the paper. The bigger the RF value is, the bigger it travels up. The ones that are least attracted to the solvent and most attracted to the paper is this one right here. This one didn't go up very far, and its RF value is low. Why? Because RF value is how far it traveled compared to how far the solvent traveled. The smaller number you have on top, if you have a small number on top divided by a number on the bottom, it's going to be a smaller number. So the ones that are most attracted to the paper, have the lowest RF value because we have a small number on top. When you divide a big number into a small number, you get a smaller number. Do RF values change depending on the solvent? Absolutely. Different solvents have a different ability to attract the colors and pull them up the paper. Chromatography separates mixtures based on molecules having different sizes, shapes, mass, charge, solubility, absorption properties. That is true. That was one of the questions right on the chromatography lab. What factors influence the ability to separate things by chromatography? All of those factors do. Nonpolar solvents are best at attracting nonpolar molecules. Yes, solvents that are nonpolar attract nonpolar colors or pigments. Likes attract likes. Letter E, in paper chromatography, the solvent is mobile. Yep, the solvent goes up the paper. The paper doesn't move, the paper's stationary. True. Why does the RF value have no units? It's because it's a ratio. Absolutely. RF values have no units because we have a centimeter on top, a centimeter on the bottom. A centimeter divided by a centimeter would factor or cancel out. So the only one of those statements that is true is letter A. If any of these explanations that we've done on any of these videos did not clear up misunderstandings, if you would like it explained differently or more slowly, or if you have additional questions you wish to ask, please do not hesitate to email me. We can set up separate Zoom meetings, help sessions, office hours, whatever it takes for you to understand these questions. Thank you for watching.